In the last class, we have been discussing the toy model that we can use to find the Helmholtz free energy density f of phi t, and the particular toy model we have been working on is the lattice model of solutions. We will take it further and discuss how can we derive the expression for f, the Helmholtz free energy density for the model of solutions, and then using that we can analyze the behavior of polymer solutions, again using a lattice model that is basically an extension of what we are doing right now. So, just to recap, the basic assumption that we have made so far is, instead of being anywhere in the three-dimensional space, the solute and solvent molecules of my model can only occupy positions on a lattice, which can be a lattice in 2 dimensions, 3 dimensions and what not. And we are assuming that there are only 2 components, a solute that I refer as P, and I will use the red color for the solute, and a solvent which I refer as S, and I am using a green color for the solvent. And these positions on the lattice are either occupied by a solvent or a solute, and of course, as we will discuss, there can be many possible conformations or configurations representing the position of the solute and solvent molecules on the lattice, and this is one particular configuration that I have just drawn. What we also assume is we have NP solvent. So, this is my lattice model of solutions. We have NP solute molecules in red color and NS solvent molecules in red color, and both of them, for sake of simplicity, are assumed to occupy the same volume, that is the volume of solute is equal to volume of solvent is equal to the cell volume of my lattice, that is the volume of any particular cell, that is of course same for all the cells, and let us say this quantity is equal to some Vc. Of course, we can generalize to different volume of solvent and solute, but that would take away the simplicity of the model has, and in any case the model is at best qualitative, because we have already restricted the motion of molecules to be on a lattice instead of being on a 3-dimensional space. So, given this particular approximation, I can define the volume fraction of solute as some phi, which is Np by Np plus Ns, or we can write Np by N total, where N total is equal to Np plus Ns. And similarly for the solvent, this has to be 1 minus phi, because the positions are either occupied by a solute or a solvent. This has to be Ns by Np plus Ns or ns by n dot. What we also assume in this model is a solute or a solvent molecule in the system only interact with its closest neighbors, that is, we ignore all the interactions with neighbors which are farther off than the closest neighbor. Of course, that will only work for very short range kind of interactions, the kind of things that we have assumed in the excluded volume theory that we have discussed earlier. And between the neighbors, they interact by, so we can say interaction energy between neighbors is epsilon pp, epsilon ps or epsilon ss, depending on what combination it is. So, for example, epsilon pp is for solute, epsilon ps for solvent, and epsilon ss for solvent. So, if we assume these values of interaction energy between closest neighbors, we can talk about the total energy of the lattice in a particular configuration, that is, for a particular arrangement of solute and solvent molecules in the lattice. And this I can write as the following: energy of, or total energy of configuration I is given as epsilon pp multiplied by the number of such pairs of solute we have which are closest neighbor of each other. So, let us call that quantity Ni pp. Similarly, for combination of solute and solvent, Ni ps, and similarly for solvent combinations, NiSS, where this is number of solute pairs, where pairs essentially mean closest neighbors. This is for number of solute solvent pairs, and this is for solvent pairs. Okay. So, this is, however, the total energy of a given configuration, and of course, there can be many possible conformation that we can find by the combinatorics, how many conformations we do have in the system. So, before we go further, I will define a quantity that is known as the partition function, using which I can discuss the free energy of the system. So, I will take a small detour and define what is known as the partition function often represented as Z, and Z by definition is the sum over all configurations the Boltzmann factor corresponding to that particular configuration, that is I. So, this is the and we have discussed earlier in the course what the Boltzmann factor is. This basically represents the probability of occurrence of that particular configuration. I will tell more about that in a moment. This is also written sometimes as exponential of minus beta EI, where beta is equal to 1 by kBt. Okay. So, essentially what Z is, if you are not used to this language, is the sum over the Boltzmann factors of all possible conformations or configurations, or what is also known in statistical mechanics as microstates. If you have had a course on statistical mechanics, you must have known this as the sum over all microstates, but essentially it is all possible conformations or configurations which are present in the system. We simply compute the Boltzmann factor and sum them up, and that is what we get is known as the partition function. So, there are two major roles of this Z in the context we are discussing, and that will suffice for the discussion that we will do in polymer physics course in general. So, the significance or the role of Z are essentially two. First one, we already have said that probability of occurrence of any particular configuration. So, probability of configuration I to occur, let us call this some Pi, it should be proportional to the corresponding Boltzmann factor. This we had discussed earlier, and so Z in some sense work as a normalization factor and why is that? Because if I simply sum over all the configurations, the Boltzmann factors, basically we get a net sum that represents the total probability of all possible conformations. And so, if I divide the quantity we have derived here or discussed here by Z, I should get the absolute probability for that configuration to occur, because we are simply dividing the probability of that particular configuration divided by the sum of all configurations, and because sum of all probabilities must equal to 1. So, if I sum over Pi, this should be equal to 1, which is of course true, because if I sum, I get something like exponential of minus EI by kBt sum by Z, which of course is equal to 1, because the numerator by definition is equal to Z. That is one use of the partition function. Another use of partition function is as generating function for other energy functions. For instance, all that means is, like, if I know Z, I can get to know all the other energy functions that I need in thermodynamics. So, for example, if I do something like that, minus dou of ln Z by dou beta, what I should have is minus 1 by Z dou Z by dou beta, and Z, as we have defined earlier, is summed of exponential of minus beta E I. So, if I take a derivative with beta, what I would get is summation over I, E I will come out with a minus sign, exponential of minus beta E I, and the z I can move inside, and this would be minus will cancel. We will have exponential of minus beta E I by z, which by definition is the probability for the configuration I, as we have derived earlier right here, and therefore, this is sum over I E I P I. So, if I multiplied the energy value for the configuration with the probability of occurrence and I sum them up, what I get is what is known as mathematical expectation or the average value. So, this gives me essentially the expectation or mean value of the energy. Okay. So, we can see from here that if I want to know the mean energy of the system, we can do some manipulation with z, and we can get that. I will not go through all the possible other variables, but the basic idea I apply, that if I know the z, I can find other thermodynamic functions with much ease. Z is the only thing I need to know. It turns out that the Helmholtz free energy, and we will see that why it turns up being the case, is equal to minus kBT ln of z, and we will demonstrate that later. And so, if I want to find the Helmholtz free energy density, which was the objective that we started with, all I need to know is my z, because if I know the z and if I know the volume, volume of course we know from the lattice model itself, the number of cells multiplied by the volume gives me the volume of the lattice. And so, knowing the z, we can get the function f. So, now the question is like, how do we find the z? So, to get z, there are of course a couple of approaches. Either we can do a simulation, look at all the possible configurations the system has, all the most probable configuration conformations, get the energies, and using that try to compute the partition function. It turns out that we do not directly get the partition function, but something of that sort. I am not getting into that. What I will discuss is what is known as the mean field theory, that really simplifies our task and give us a good analytical expression for the z, partition function z. So, the mean field theory, and of course, just like the name says, the mean field, it is actually an approximation than being exact, and the approximation is that what we assume is, instead of the different conformations having different energies, we assume that all the conformations have a mean energy E bar. Okay. So, the assumption is like all configurations have mean energy E bar, because if I do that, then Z, which was summed over all the Boltzmann factors. Now, if all the EI, is approximated to be equal to E bar, then this is simply exponential of minus beta E bar, which then would be something like W multiplied by exponential of minus beta E bar, where W is the number of possible configurations, and we know that what it is. So, we have NP solute molecules, NS solvent molecules, the number of ways to arrange them on the lattice is given by simple combinatorics, and it is equal to the number of possible conformations. The W is NP plus NS factorial by NP factorial NS factorial. Although we have taken example of solute and solvent, you can think of apples and oranges. The number of ways to arrange the, say, 5 apples and 10 oranges on 15 sides is given by like 15 factorial divided by 5 factorial multiplied by 10 factorial. This is the standard formula we had in combinatorics. So, we know what W is. The only challenge is how to get the E bar. Okay. So, we have already said that my EI is epsilon PP multiplied by NIPP, where NIPP is the number of solute-solute pairs and epsilon PP is the interaction energy between the molecules in that pair. The same thing for solute-solvent pairs. And same thing for solvent pairs. So, E bar has to be average of that, where N bar is now the average number of pairs, N bar PP is average number of solute pairs, N bar PS is the average number of solute solvent pairs, and N bar SS is the average number of solvent pairs. And these quantities we can get by simple probability rules. So, we know that each of the sites can be occupied by the solute with a probability phi, and then let us say that particular site is occupied by the probability phi, then it has Z neighbors, small z neighbors, where Z is the coordination number, and they can be a solute also with a probability phi, because phi is the fraction of the solute molecules in the system. So, if I think of any position on the lattice, let us say I look at this particular position, it may contain a solute molecule with a probability of phi, and this will then have z neighbors, small z neighbors, which is equal to 4 for square lattice, and each of them can also be a solute with probability phi each. So, if I multiply phi with z phi, I get the total number of the total probability of having a pair of solute and solute in a given site, and this if we multiply with the total number of sites, I should get the total number of such solute pairs in the system. The only thing is that if I am doing this way, I always do a double count, because when I come here, so when I now come here and look at the neighbors of this guy, then we will again find that this also has 4 neighbors. One of them that is already counted, and so we always have a double counting of the pairs if we proceed in the way I have suggested. So, we have to divide this by 2, where 2 accounts for the double counting, and this is then 1 by 2 and tot z multiplied by phi square. The same thing applies for a solvent pair, except that now the probability to find a solvent on a given site is 1 minus phi. Again we have z neighbors, and they can also be a solvent with a probability of 1 minus phi. Again we have double counting, and now what we get is this. The same idea can be applied for a solute solvent pair. So, now every site can be a solute with a probability of phi, and then it can again have z neighbors, which can be solvent with a probability of 1 minus phi. This time we do not have to divide by 2, because we are looking at pairs of different species. So, I am looking at the solvent neighbors of every site. So, if I go to the next site, again I will look at solvent neighbors, assuming that the site is occupied by the solute. So, in this case we do not have any double counting in the picture. So, using these 3 formulas, I can plug that in the equation for E bar, and what I will get is the following. Is this. So, of course, n tot and z can be moved outside, also the 2 there, and what we get is phi square epsilon pp plus 1 minus phi square epsilon SS plus 2 phi into 1 minus phi epsilon of PS. So, with this I stop here. In the next lecture we will take it further and go on to find the expression for the Helmholtz free energy density for the lattice model, and using that we can then extend and talk about the mixing and phase behavior that we have discussed earlier, now given the functional form of the Helmholtz free energy density. So, with that I stop here. Thank you.